Here's a problem that every student loves. A soup can in the shape of a right circular cylinder is to be made from two materials. The materials for the side of the can cost 0.015 per square inch, and the materials for the lids cost 0.027 per square inch. Suppose that we desire to construct a can that has a volume of 16 cubic inches. What dimensions minimize the cost of the can? So it's fabulous that we read through that. Yippee, hooray. But what we have to do now is pull it apart so that we figure out what we have and what we want. I always look at this last question. What dimensions minimizes the cost of the can? Since this is optimization, we have to figure out what it is that we're going to optimize, and we're minimizing cost. So I have to find a formula for cost. Because it says it right there. I have to minimize that. But what else am I given? I know that the material for the side is 0.15 and material for the lids is 0.27 per square inch. Square inch also implies area, square inch. So if I draw a picture of my right circular cylinder, it's like an oatmeal canister. I know that this is going to be H and this is going to be R. And I know that the sides are going to cost $0.015, and the tops, or the lids, I guess is what they say, is going to be 0.027. Now it also gives us the volume is 16 cubic inches. So the volume is 16 cubic inches. Now, we can come up with a formula for cost. We can come up with the formula for volume for this right circular cylinder, because those are the two things we want and what we're given. Okay, now let's just start with the volume of a right circular cylinder. According to definition, it's going to be the area of the top, which is pi r squared, times the height. And we expect that volume to be 16 inches because that's what's given to us. Write it down. This is an important thing that's going to help us when we do get what we want. Now over here for the cost, it talks about it costs a certain amount per square inch, and square inch implies surface area. So we have to put together the surface area and the cost per square inch to come up with this formula that they want. So cost, if I think about the area of the lids, there's going to be two lids. Each one has an area of pi r squared. And every square inch in those lids is going to cost me $0.027. And if I think of the side, remember if you cut this down the side and laid it flat, it would be a rectangle whose height is h and whose length is going to be the circumference of a circle, 2 pi r. And that, the square inches of the side of the can is going to cost us $0.015. So let me move this over just a little bit. That's our cost function, and we can simplify that really nicely if we just take a couple seconds. Where'd my calculator go here? So if I take 2 times 0.27, 2 times 0.027, I get 0.54 pi r squared plus 2 times 0.015, 2 times 0.015. That gives me 0.03 plus 0.03. So I did those two numbers, pi r h. So there's our cost function. Now, what we normally do with a function when we're dealing with optimization is we take the derivative of it with respect to the one variable that's there. However, we have two variables. We have an r variable and an h variable. Well, that's when we come back over here and we use this to restrict the behavior of one of those to match up with the other variable. So here I actually do have a relationship between r and h. It's easiest to solve for h, so that's the way I'm going to do it. It's h times this, so if I want to do that, I have to divide by pi r squared. So now I have a direct relationship. As r grows, h shrinks. As h grows, r shrinks. It's an inverse relationship. However, all I have to do is stick this in for h right over here, and now my cost function suddenly becomes a function of one variable alone, and that's really a big deal for us. So I'm going to put that in there, 0.54 pi r squared plus 0.03 pi times r times h. Keep simplifying, and I get 0.54 pi r squared. Yeah, I got to be careful here. There's lots of zeros here. And I just noticed an error that I made. So I'm actually going to just rewrite this over. The error here, I need to actually have a 0 after the decimal place like this. Same thing up here. That can easily cause all kinds of trouble when you look at the product here. 2 times this is 0.054. 2 times this is 0.03. So it's got to be 0.054 and 0.03. Man, that's such an easy mistake to make. You got to be very careful. My cats are in the other room making all kinds of noise. So C of r then, if I keep going, I need to simplify. I'm glad I realized that. 0.54 pi r squared plus 0.03. Now these pi's cancel. And I left off that r there, so that r cancels. And so this is going to be 16 divided by r. And so then I can multiply these two numbers together. 0.03 times 16. 0.03 times 16. 0.48. Make sure I did that right. 0.48 over r. And that over here is 0.054 pi r squared. All right. That is the function that we have to optimize. We also need to think about the biggest and smallest r can get. So theoretically, the smallest r can get is really close to 0. And as r gets really close to 0, h gets close to infinity. And as h gets close to 0, r gets close to infinity based on this inverse relationship. So r is going to be bounded by 0 to pi. Now all we have to do is just take the derivative and find the critical points and see what happens at the endpoints, or these end values, and then we have our optimization done. So now we're going to find C prime of r to find the critical points. So C prime of r is equal to, let's see, I bring down the 2, so it's 0.054 times 2. 0.054 times 2 gives me 0.108. So bring down the 2, so it's 0.108 pi r minus 0.48 over r squared. Now I have to see where that equals 0 to find critical points. 0.108 pi r minus 0.48 over r squared. I can add this number to both sides. 0.48 over r squared is equal to 0.108 pi r. Cross multiply now. So think of this as being over 1. That's going to look like 0.48 is equal to 0.108 pi r cubed. If I continue to solve for r, I'm going to divide both sides by this number. So r cubed is equal to 0.48 divided by 0.108 pi. And then I take the cube root of both sides. I know this is ugly, but it doesn't matter. This is it. And I don't need the plus or minus because it's cube root. Now I'm going to use my calculator. I'm going to do 0.48 divided by 0.108. And I want to come up with a fraction for that. And that's 40 over 9. So that means that this is going to be 40 over 9 pi. So there's my one critical point. So I need to evaluate C at that critical point. Remember, when you do this, you go back to the original function because we're not finding local maxes or mins. We have to look at the limit as r goes to 0 of C and the limit as r goes to infinity of C. Those are the end points. These are end, and this is the critical point. Now, when you do this, I would do it approximately. I mean, it would be really hard to do by hand. So I'm going to come over here into my y equals, and I'm going to input into it my original C of r function, which is right here. So 0.054 pi x squared, because I can't use an r because, you know, this is a simple calculator, plus 0.48 divided by r, or x in our case, because that's all we got. After doing that, I go over to my table, and I'm going to put inside the table my r value. So it's going to be 40 divided by 9 pi. Remember, the parentheses are important. Raised to the 1 divided by 3, because that's how you do to the cube root. And you notice when I plug that in, I get 0.64137. 0.64137. Oops, let me write it down. There we go. And now, if I think about these limits, I want to look at the graph because that's easier to tell. And if I do my window, I want to go from 0 to 10. And I want to go from 0, because y is the surface area of the cost, and it's not going to be negative. Y goes from, well, let's see what happens to my function at 10. I'm at 17, so I'm going to go up to 18 here. Graph it. There it is. So you can see the minimum right here. And you can see as I go towards 0, this goes up to infinity, and then I go towards infinity, that goes. So that is definitely the only critical point. So this goes to infinity, this goes to infinity, so this is the global min. So for that R value, I get that global min. So let's answer the question. The question says, what dimensions minimizes the cost? So the dimensions that minimize the cost is a radius of approximately, I have it in here, approximately, oh, I got rid of it. Oh, bummer. Let's put it in again. 40 divided by 9 pi raised to the 1/3. And I get points. Oh, I'm sorry. I need this number. 1.1226. 1.1226. And then to get my height, I have this relationship right here. So I'm going to come back down and put 16 divided by pi times 1.1226 and calculate that number. 16 divided by pi, oh, this should be squared too, by the way, pi times 1.1226 squared. Well, let's do it this way. Just to make sure we don't do anything silly. Let's delete that. And then that. So that closes off that. I need one more close off that guy. And this should be 16 here. So my height is going to be 4.0413. So H is 4.0413. So those are the dimensions that minimize the cost of the can. I know if I went really fast, I'm sorry. I do have the PDF available so you can take a look at it.